program coordinator. So we have a speaker today from Yadav. And I feel extremely privileged to introduce our today's speaker. Dr. Nitin Yadav has done graduation from University of Bikaner in 2007. And after that, she has completed MSc Physics from University of Chandigarh. And in 2011, she has completed MTech degree from IIT Delhi in laser matter interaction. In 2015, she has completed PhD in space plasma physics from IIT Delhi. And after that, she has joined research associate postdoc in IIT Delhi. Between 2015 to 2017, she was the associate professor, research associate. After that, she has joined postdoctoral fellowship in Max Planck Institute for Solar System Research, Germany. After that, she has joined as a postdoc in KU, Belgium, and currently she has been appointed as an assistant professor in IJR Trivandrum. Her area of research is magnetohydrodynamics theory and simulation, solar atmospheric and radiative transfer, Bayes and mode transforming process, solar plasma, dynamics and heating, space plasma physics, magnetic reconnection, and energetic events. She has a lot of scientific collaboration with the Professor Ronnie Keffens from KU, Belgium, Professor Sami Solanki from Max Planck, Germany, Dr. Robert Cameron from Solar Dynamo Max Planck Research, Germany, Professor R.P. Sharma from IIT Delhi, and there are so many esteemed members in the field of plasma research. And she has published more than 50 publications in international national journal of repute. So, we already yes, ma'am. So I am welcoming you in the 12th lecture of physics on Friday. Over to you, ma'am.
Okay, thank you very much, Sintu, for the kind introduction. So I would like to share my screen now and start my presentation.
Yeah.
Okay, so I hope you all can see my screen and also hear me well. So as Sintu mentioned, I'm Nitin, and I have recently joined as assistant professor in IISER Thiruvananthapuram. And I'm very glad and very obliged to you for inviting me to share my work with you and also to talk to you. So let's begin. So I'll begin with some basics about solar physics, because maybe not all of you are aware of this research field. So I will spend a few minutes about what this research field is and what do solar physicists actually work on. So in this screen, in the slide, already you can see some animations, which are movies of images recorded of sun in different wavelengths. So looking at these animations itself, you can see that sun is not like a fireball that is continuously emanating radiation and energy, as we were told in our childhood. At least I was told like that. So sun is much more variable and evolving and dynamic than what we used to think. Okay, so and the spatial and temporal scale over which the physical processes take place on the sun that have a broad range of spectrum. So for example, there are physical processes that take place on the spatial scale of less than a centimeter and less than time scale of microsecond. And at the same on spatial scales of megameters and over a course of a few years time scale. And scientists or solar physicists who work in this field, they are interested in various processes. They may be large scale, they may be small scale, depending on the physical phenomena that they are interested to study. Okay, and then comes the question: why do we actually need to study sun? Right. So sun is doing its job for billion years now, and it's already a middle-aged star, so it has spent like halfway through its life, and it will continue to do its job for the next 5 billion years more, that we know. So why do we need to study how many processes are happening there, or what all physical mechanisms are taking place there? So there are two main reasons in my view. So the first one is that we exist because of sun, okay? Or life on earth is actually sustained because of the light, heat, energy that we get from the sun. So naturally, we are interested in investigating or studying the source of our existence. And also, we can use this information to apply on other stars, which are much further away from us, not like sun, which is the closest star. So we can apply the knowledge that we learn from the sun to other stars and see what are the conditions for a star to have a habitable planet, or why is sun so special that is the only star out of the billion stars that has a habitable planet that is orbiting around it. So that is one reason. And the second reason, the most important reason these days, is that now we are in an era where we are extremely technology dependent. So we cannot even like imagine our life without telephones or mobile phones, television, or without internet, right? So we are greatly relying on technology these days. And the processes that happens on sun, sometimes they can be so strong that they can disrupt these telecommunication devices. So we need to understand processes happening on sun, because they can sometimes be so dangerous, so harmful that they can affect our telecommunication. So that is these are the major reasons that scientists are interested in investigating solar physics or processes that happens on the sun. So here I just shown some movies to show you what kind of explosive events happen on sun. How do they look like? So on the left, we have a zoomed in view, like it shows a part of the solar atmosphere on the solar surface where a solar flare is happening. So solar flares are happen because of the magnetic reconnection process, and magnetic field reconfigures and a large amount of energy releases. Okay. And on the right hand side, the field of view is comparatively much larger. So here we see that the solar flare that happens in the solar atmosphere doesn't have impact near solar atmosphere. It also affects the interplanetary space. Okay, so the energetic charged particles that are released after this process, they propagate through the interplanetary space, and whatever planets and other bodies are there, they will get influenced by these highly energetic radiations and particles, including Earth. So to get an estimate like how much energy is actually released, okay, so in terms of numbers, in a typical solar flare, the energy that is released is of the order of 10⁻20 to 10⁻25 joule. But these numbers may not make much sense to us because we don't have a physical idea of how much energy that is. So you can compare it to like a typical solar flare's energy is equivalent to if 1 million of 100 megaton hydrogen bombs are exploded all together. So that is the amount of energy that each solar flare produces. And then this vast amount of energy will be propagating through the interplanetary space whenever there is a flare. But when does it matter to us? Because these solar flares and these CME ejection that will be happening throughout the solar surface, right? Or throughout the solar atmosphere. But for us, it mostly matters when it is directed towards Earth, because then all these highly energetic particles and radiations, they are traveling towards Earth, towards our planet. And although our magnetic field will be there to save us from that, but sometimes these energetic radiations can be so strong that they can still have harmful impacts on the telecommunication devices and satellites. Okay. But there are some positive side effects also of these solar flares and CMEs. For example, polar lights. So what are polar lights? Polar lights are the colorful wavy patterns that usually occur in the north and the south polar regions. And the physical mechanism behind these polar lights is the interaction of incoming energy particles from the sun and the magnetic field of Earth. Okay, and when they interact, they create these colorful lights on north and south poles. But apart from this, if the incoming CME, the coronal mass ejection, is too strong, it's very highly energetic, then it can have some dangerous impacts. For example, it can disrupt our satellites which are there in the space. It can disrupt the telecommunication devices. So our phones may not work, our television may not work, there can be complete blackout. And also, if there is a CME and we have our astronauts in the space that time, then it can be life-endangering for those astronauts. So that makes investigating these processes happening on the sun more and more important. Because if we can develop such models which can predict that when there will be a solar flare or CME, then we can try to minimize their impact on Earth. So this was all about the motivation to pursue this field. But how do we get this information? Like, how do we study sun? So of course, we cannot just look directly at the sun and study sun. Because first thing, because there are harmful radiations, there are UV, EUV radiations that mostly will be blocked, but still some part of it can still reach Earth. And if we look directly at the sun, then they can spoil our eyes. So of course, that is not the way, but we can use telescopes or filters to investigate sun. So what we require is multi-wavelength observations of the sun. Why do we need multi-wavelength observation? Why not a continuum or a fixed wavelength? That will come later. So, for example, here we have I have shown the full range of electromagnetic spectrum, ranging from gamma rays, X-rays, up till radio waves. Okay. And if we want to study human body, if we want to see, is there a fracture in a bone or something, we go to X-rays, right? We take X-ray and we look at the skeleton. But if we want to just see the usual features, if we just look at invisible range, then we just see a person's features, complexion, hairstyle, those things. Okay. And at the same time, if we want to look at the temperature variation, then we go to infrared part of the electromagnetic spectrum. So we can see just in human body, going from different wavelengths, we can get different kind of property, different information about humans. So the same way for the sun, if we go from different wavelengths, they actually map different parts of the sun, different layers of the solar atmosphere. So to get a full-fledged information about the solar atmosphere, we need multi-wavelength observations. For example, here I have shown various AIA channels, so which are maps of intensity particular to a fixed wavelength. Okay, for example, this is 1700 angstrom, which is originated from photosphere. This is 304, which is originated from transition region. These are 193 angstrom line, which is originated from corona. So looking at images of sun in different wavelengths is actually mapping different parts of the sun. So we cannot have directly a three-dimensional view of sun in observations, because we are only relying on the photons that are coming from the sun. And from our theoretical knowledge, now we know which photons are originating from which part of the sun. For example, we know that if we are talking about silicon 4 line, it is originating from transition region. If we are talking about iron 9 line, it is originating from solar corona. So depending on different wavelengths, we can map different parts of the sun and study processes that are happening in those parts of the sun. And how do we get these images? These are, we need to use some backend instruments like imager, polarimeter to get magnetic field information, spectrometer, spectrograph to get spectra. And these are associated with the telescopes. And those telescopes can be ground-based telescopes, like they can be put on surface of the Earth, or they can be space-based telescopes. For example, they can be they can go outer space and then take images of the sun and record images and other data from the sun. Or actually, in these two, ground-based telescope are comparatively less expensive to build and it takes less time to build. But the problem is because they are on the Earth, they suffer from the resolution because of the atmospheric turbulence. The images, the quality that we get is not that good as we get in the space-based telescope. But on the other hand, space-based telescope need a lot of time to build. This currently takes 10 to 15 years to make a space-based telescope, and it's much more expensive as well. Something between these two is stratospheric balloons. In that, what we do, we attach our telescope and other instruments to a balloon, and then we release it such that it goes out of the Earth's atmosphere and reaches to stratosphere. And in stratosphere, the conditions are much more stable. So there we are not suffering from the atmospheric aberration. So the quality of the images that we get is comparatively much better. And similarly, we can use planes so that we can put telescope and send it through planes or sounding rockets. So these are different ways to get observations of sun. So until now, I was talking only about observations, but we can only use observations to study surface and atmosphere. For example, we cannot see through the surface. We cannot get any information what is happening beneath the surface. Okay. And also in observations, we are limited by spatial, spectral, and temporal resolution. Okay. Because as we make this telescope bigger, we are improving spatial resolution, but at the same time, we are increasing the cost and the maintenance and other issues. So it is not possible to achieve a spatial resolution to the extent that we want. Whereas if we use simulations, numerical simulations, that we can actually mimic sun in our computer. So we can perform numerical simulations and make conditions such that it is actually replicating these processes that might be happening on the sun. So currently there are various radiation MSD simulations, which are realistic simulations, and that have been developed by various research groups around the world over a time scale of 15 to 20 years, because these are very difficult to develop, because you have to include a lot of comprehensive physics to actually realize the processes that are happening on the sun in a realistic manner. So one such code is called Muram code, that is mostly developed at Max Planck Institute for Solar System Research and at High Altitude Observatory in Boulder. So I have used this code along with another open source MSD code called MRVAC to study the solar atmospheric heating problem. So now I will tell you a little bit about what is this solar atmospheric heating problem. So the image here displays how the temperature varies from the distance from the core. So at the core of the sun, we know that the fusion reaction is taking place, how the four hydrogen atoms make helium. And in the process of this fusion, there is change of the mass that is converting into energy, and then the photons propagate. Okay. So there the fusion reaction, the energy source is at the core. Therefore, the maximum temperature of the sun, that is 15 million Kelvin, is at the core. And as we know from our day-to-day experience, that as we go away from the heat source, temperature decreases because energy is being used in heating the material on the way. So the temperature goes down as we are going away from the core. But as you reach to the surface, temperature has dropped down to 5,700. That is the surface temperature for the sun. But what happens after reaching the surface is contradictory to what we would assume. Okay, so temperature starts to rise again. And if you look at this small portion in this zoomed view, you can see that the temperature is increasing again. And then the temperature is around 7,000 Kelvin here. Okay. And if we keep on continuing, then in corona, the temperature has reached to million Kelvin temperatures. So, so this increase in the temperature is still one of the unsolved problems since decades in the field of solar physics. So we don't know what can be the physical mechanisms that are taking place in the solar atmosphere, which are causing this excessive heating only in the solar atmosphere. So that what we call as a solar atmospheric heating problem in solar physics community. So to get some idea what can be the physical mechanism responsible for this excess heating, I am showing here a few movies. So the left one is an animation by recorded by AIA channel 304. The middle one is AIA channel 171, and the rightmost animation is from HMI magnetogram. So the first two gives us information about hot plasma. The first one corresponds to the plasma that is around 50,000 Kelvin. The second one corresponds to the plasma that is around 500,000 Kelvin. And the rightmost tells us about the magnetic field profile. So one thing is very clear from if we compare these simultaneous movies, that when there is hot plasma, it has simultaneous magnetic field strength. So there are strong magnetic regions where there is hot plasma. So it indirectly indicates that there is some correlation between heating and magnetic field on the surface. But how exactly magnetic field is causing this heating, that we still don't know. So the two most plausible candidate mechanisms for this heating are magnetic reconnection and MSD wave dissipation. And in both these methods, the key ingredient for heating is the turbulent surface plasma flows, and magnetic fields are actually a medium for the transport of energy. For example, the movie here displays shows you the 10-minute of solar surface evolution with the highest resolution that we can achieve today, which is 30 kilometers on the solar surface, and it is recorded by DKIS, ground-based telescope, which is the largest telescope at date with the diameter of 4 meters. So here you can see that plasma is continuously evolving. And although in this movie, we don't get any information about magnetic field, but from other observations, we know that magnetic field is actually rooted in these dark lanes. And when these are the regions of the sun where plasma beta is very high. So if plasma beta is high, the magnetic field is just frozen into the plasma flows. And wherever plasma flows are moving, that they will take the magnetic field with them, right? And since these are turbulent motions, so these motions are spanning a wide range of time and spatial scales. So they can be large time scales, large spatial scales. At the same time, they can be smaller time and smaller spatial scales. So in these two extremum conditions, when the time scales are very large and the spatial scales are also large, they can twist and tangle the magnetic field lines in such a way that it leads to a configuration which is like very stressed configuration, because magnetic field is nothing but like rubber bands, right? So if there are like rubber bands and we are twisting and churning them continuously for a long duration, you know what will happen? Like it will go to a state where it is like lot of stress and very high energetic situation. So in that case, it will try to reconfigure. Magnetic field will try to come to a state which is less stressful configuration, and in that process it releases the amount of energy which is the difference between the older configuration and the new configuration. This I have shown here by this cartoon. So if the configuration changes and the new configuration has a lower energy, then the difference of this energy will be released in the process of magnetic reconnection, and that can heat the plasma there. So this is one method, and the another method is wave dissipation. So if these plasma motions are of small spatial and temporal scale, then they can just give these magnetic field lines a small jerk, a small perturbation. And then this perturbation will propagate upwards in the form of MSD waves. And as these MSD waves propagate, they can somehow get dissipated because of physical processes like Landau damping or resonant absorption or other mechanism. And when they get dissipated, energy will be converted to heat. So this is another method of converting, like how magnetic field can help in transporting energy from the solar surface to the higher layers. Now coming to my my work. So I have used Muram code, that is a box in a star kind of simulation code. And what I mean by box in a star is, so for example, you have this magnetogram. It is giving you information about the magnetic activity on the sun. So the gray part is quiet sun, where there is very less magnetic activity, and the mean magnetic field will be around a few tenths of Gauss. Whereas this dark region and this bright region, so they are called strongly active region or plage. So here the magnetic field strength can be a few kilogauss. Similarly, there are other magnetic configurations, for example, magnetic network and decaying active region. And if we want to simulate some of one of these configuration, what we do is we put a simulation box, a rectangular box on the surface of the sun. Okay, and then we try to and we give the dimension to this box according to our requirement, according to our numerical computational capabilities. For example, I am interested in small scale features. For example, I want to investigate how the small scale tornadoes or the small scale vortex flows evolve in time. Since I'm interested in structures that are a few kilometers, I have to take spatial resolution at least 10 or 20 kilometers, right? Only then I can study processes that are happening in those scales. And that if I am restricted by the resolution I want, I cannot go to a very large domain of the simulation box, because then it will be very difficult to do the analysis afterwards. And first of all, to run the simulation, it will take several months. Okay, so in that case, we need to first think which problem are we interested in, what are our spatial or the temporal requirement, and accordingly we choose the dimension of the simulation box. And then we put this simulation box here, and according to our interest, if we want to study quiet sun or plage region or decaying active region, bipolar region, network region, according to that we give the magnetic field profile in the simulation box, and then let the system evolve to a realistic kind of situation. And what this code actually does is it solves radiation MSD equations. And we have also included 11 most abundant species on the sun to calculate the equation of state. And we also use hyperdiffusivity to make the code stable. And the most important thing is the open lower boundary conditions, which maintains constant entropy as it should be in the convection zone. And it also allows free inflow and outflow from the bottom boundary. So these are some of the technical details of the simulation code. Now coming to the vortex flow or the rotational flow part. So as I mentioned, this solar surface is a turbulent medium. And just like any other turbulent medium, there are rotational structures like vortices, which must be present in all turbulent fluids. So there are vortex flows present on the sun surface as well as in the atmosphere. For example, and there have been some direct observations of these rotational flows. For example, on this slide here in this image on the right, you can see imprints of rotational flow in different heights of the atmosphere, right? And these rotational flows are actually associated with excess heating also. So there were some conjectures that maybe these rotational flows are exciting some waves, or somehow they are heating the solar atmosphere, because these rotational flows are very much abundant and ubiquitous on the solar surface. So in observation, since we don't have three-dimensional information of magnetic field vector and velocity vector, we cannot actually see the physical mechanism that will be causing heating, because we can see through images that there is some rotational feature and there is some excess heating, but we cannot do a lot of analysis to look for the physical mechanism that are leading to that heating. But in simulations, we can have high precise information about the velocity vector and magnetic vector, and then we can perform more detailed analysis to look for the physical processes. So that was my aim in this research problem. So I wanted to study what are the characteristics and nature of the vortex flows that I will find in my realistic simulations of a plage region. Now again, how do we perform simulations? So I chose, as I mentioned earlier, that we choose a simulation box. So in this case, I chose a box with the dimension 12 by 12 megameter square and 4 megameter in height, which was such that it was 1.5 megameter below the surface and 2.5 megameter above the surface. So it extends from a part of the upper convection zone up till the transition region. And then we took the resolution such that this box is discretized by 1200 by 1200 by 400 grid points, so that in all the three directions, I have a grid spacing of 10 kilometers. So my each grid cell corresponds to 10 by 10 by 10 kilometer cube. Okay. And to start the simulation, we ran it for hydrodynamic case. So there is no magnetic field in the beginning. We ran it for hydrodynamic case and let the system reach to a quasi-stationary state. And when that has reached, then we input magnetic field. So in this case, because plasma is strongly magnetic part of the sun, we introduce a vertical magnetic field of 200 Gauss and let the system evolve again to reach to a quasi-stationary state. And when it has reached there, we collect data for the analysis. These are some of the snapshots, some of the results from the simulations after it has evolved for the sufficiently long time. So on the top row, on the left hand side, you have vertical component of magnetic field strength, and on the right, you have vertical component of velocity. So in the left hand side, you can see that we can still see the granulation pattern, and similarly on the right. And on the left, the parts which are deep red color, so those are the regions where the magnetic field strength has reached to kilogauss magnetic field strength, which is typical for a flash region. And but also there are some mixed polarity region, this red and blue things. So those are small scale mixed polarity stuff. So these kind of information we cannot get from the observations because these are really small scale things. I have resolution, a spatial resolution of 10 kilometers, which we cannot achieve in observations. And also to get information of magnetic field from observations is non-trivial. So these kind of information we can only get through numerical simulations. So in the bottom row, I'm showing here the map of intensity. And if you zoom in a small part, you can see these ribbon-like structures that are also very typical of flash region. So this is just to show that quantitatively as well as qualitatively, through this simulation, we can realistically simulate actual solar conditions for flash. So this is just to show the time evolution. In the previous slide, we show one snapshot at one particular time instant, but how things evolve with time. So on the left-hand side, again, you have vertical component of magnetic field strength. On the right-hand side, you have vertical component of velocity vector. So on the left, you can see that although the magnetic field strength is reaching to kilogauss values, it is strongly magnetic. These are not stable. They are not staying at one location. These magnetic fields are continuously moving around. They are evolving. And on the right hand side, you can see like the regions where there is a lot of magnetic field strength. It is still turbulent. So there is turbulent flows underneath and there is strong magnetic field. So these are the typical locations where we can get a lot of torsional elephant waves and the vortex flows. But how to detect these vortex flows? So now we know, okay, there is, this looks very realistic like flash region. It looks turbulent. So there must be vortices present, which have been observed in observations. But how do we detect it in our simulation box? So one very simple way of detecting vortices could be that we calculate vorticity, right? We have velocity vector information in the full cube. We calculate vorticity and the locations where there is a lot of vorticity, that can give us the location where there will be a vortex present. And many people have done this in literature. But the problem with this method is, like many times there can be such situations that there are oppositely directing flows. So there is flow going in one direction and in neighboring region there is flow in the another direction. So on their interface, the vorticity will be very high because these are oppositely directing flows. But it doesn't mean that that is a vortex because there is no true rotation there. So therefore, we use an improved method that is proposed by Huang et al. in 1998 in a mathematics paper. So what they suggest is that instead of calculating vorticity, we should calculate velocity gradient tensor at each grid point in the simulation box. And that 3x3 matrix, and we perform eigenanalysis of that at each grid point. So we will get 3 eigenvalues and correspondingly 3 eigenvectors. And only those locations have true rotations where the eigenvalues are complex conjugate to each other. And I use that method, and then we look for structures which have at least 200 grid points in each structures so that we can get rid of the transients. Because sometimes there can be a structure which has just 4 or 5 grid points and that follows this criteria. So that is not an ideal case for us to study. So we were only interested in structures which have a good amount of material in that rotating, and then it follows the criteria which I just talked about. So in this image on the left here displays the 3-dimensional views of these vortices which are selected by this method. And the background maps shows the continuum formation layer where the continuum is formed, which is color coded with the magnetic field strength. So you can see one thing, that all these vortices which are detected, they are rooted in these strong magnetic field regions. Okay, so there is a connection between strong magnetic field regions and the propagation of vorticity to the higher layers. And if we zoom in one of these small regions and we plot the velocity streamlines, then we can see that plasma is in fact rotating along these features. Here, the sea green lines are corresponding to velocity streamlines. The purple is the background magnetic field. But these structures which we found here have a spatial scale of a few kilometers, like a few tens of kilometers. But these kind of vortices are not yet detected, of course, because of the spatial constraint. But in observations, the vortex flows that are detected have a dimension of around 1 to 2 megameter. Okay, but in our simulation, initially we didn't see those vortices. We were only getting to see small scale vortices, but not the larger scale vortices. So my next quest was that why don't we see these large scale vortices in these simulations? That we understand the other part of the story, that in observations we don't get to see small scale vortices because of the spatial resolution. Then in observations we don't have that resolution, so we cannot detect small scale vortices. But in observations we get to see large scale vortices, which I couldn't see in my method. And the reason was that all these vorticity detection method, they take gradients. So they only detect the stronger part of the vorticity, and the stronger vortices are the smaller ones, not the larger ones. But to get an idea of these large scale vortices, what I did is I degraded my simulation data to a coarser resolution. So for example, the image here that you are seeing is produced with the resolution of 500 kilometer. So here the spatial resolution is not 10 kilometer as it was in the actual simulation. I degraded it further by convolving my simulation domain with the Gaussian kernel with full width half maxima of 500 kilometers. Okay, and now you can see just by eye, you can see that there are bigger rotating structures. The white color arrow here displays the velocity vectors, horizontal velocity vectors. So we can see that there are larger vortices present in our simulation balls, but we didn't see these larger scale vortices when we were using high resolution or the full resolution data. But now next I wanted to see, like, are these large scale vortices actually related to the small scale vortices, or they are completely independent? So for that, what I did, I selected this one vortex in the degraded simulation, degraded data, and then I looked at the same region in comparatively high resolution data. For example, this is for 500 kilometer. These arrows are showing horizontal velocity vectors, and the background maps is telling you swirling strength. That is a rotational velocity. And now if we look at the same region in 100 kilometers, we can see that now instead of one vortex, there are many more vortices, right? This is the same area of the sun, but now there are much more vortices present. And now if we go to even better resolution, which is the actual resolution of 10 kilometers, then there are numerous vortices. So the same area where there was one vortex present in poor resolution is actually consisting of thousands of vortices if we go to better resolution. So there is a substructure of each vortex that we get to see in these simulations. So based on that finding, I made a cartoon here to understand it. So in the top panel, we have a single vortex. So this is how we see in the observations. Because we see because of the spatial resolution constraint, we cannot see small scale structures. So we see an averaged result. So we see only a large scale vortex flow, which stays there for a longer duration for 5-10 minutes. But if you have high resolution at your disposal, in that case, you can see its substructure also. So you can see small scale vortices within these large scale vortices. So all these vortex flows that are detected in observation, they actually have a substructure present. So next, the way forward was to see which of these vortices are actually more important from an energy point of view, right? So we know one thing, that these vortices are aligned with the magnetic field. They must be transporting energy from the solar surface to the higher layers. But which of the vortices, the small scale vortices or the large scale vortices, are the dominant contributor to the energy transport. So for that, what I did is I calculated total vertical Poynting flux, so total energy flux that is going upward. And I did it for 3 resolutions. First one is the solid curve here in this panel, in the top panel, that corresponds to the full resolution, 10 kilometer. The dotted curve is for the 50 kilometer resolution, and the dashed curve is for 100 kilometer resolution. And it is showing you variation with height of total vertical Poynting flux. So you can see that as we are getting better and better resolution, in full resolution, that is 10 kilometer, the amount of Poynting flux, the amount of energy is much more. So which tells us that small scale features, small scale processes are actually a major contributor of energy, right? So most of the energy is being transported by the small scale features, because those things are not available when we degrade it. In the degrading procedure, in the averaging procedure, that information is getting lost. So that part of the energy is not available in this dotted and the dashed curve. So one thing is clear that, okay, small scale features are important, but there are various kind of motions. There are vertical motions, there are horizontal motions. Which of the plasma motions are dominating? So we separate the total vertical Poynting flux in 2 components. So one is generated by the horizontal plasma motions, and the other one is by vertical plasma motions. So here the pink curve corresponds to the horizontal plasma motion, and the blue curve is for vertical plasma motions. So here also, like you can see that the contribution by the horizontal plasma motion is positive, whereas the other one is negative. So the energy that is going upward is mostly because of the horizontal plasma motion. And horizontal plasma motion are actually dealing with the rotational plasma motions. So this also indirectly or implicitly tells us that rotational flows or the vortex flows might have a strong contribution to the total energy that is going upwards from the surface. And finally, the next I wanted to see like how the spatial resolution actually affects that. Now we are at 10 kilometer, but how much are we losing by not going to, let's say, 5 kilometer resolution or 2 kilometer resolution? So I degraded data, and then at different heights, I saw how the variation fits like. So it actually follows a power law kind of behavior. And here you can see that we are gaining a lot of information going from 50 to 10 kilometers or 100 to 50 kilometers, but going from 10 kilometers to even 5 kilometers or 2 kilometers is not, we are not gaining much. So 10 kilometers is quite a reasonable resolution that we are dealing with. So next, it was clear that, okay, small scale vortices or small scale features are important, but are vortices important or other features important? So therefore, I did similar analysis only on the locations where vortex flow was present. So the top curve shows you the Poynting flux on the location of vortices, and again for 3 resolutions. So you can see the 10 kilometer resolution, which is the full resolution of my simulations, gives you the highest value. So this is the resolution in which we had small scale vortices present. Whereas the degraded resolution is that part where the small scale vortices were not present and only the large scale vortices were present. Comparing these 3 curves, we can see that small scale vortices are actually a dominant contributor to the energy transport. And this panel B compares relative Poynting flux over vortices and also their area coverage. So red curve is the area coverage. So if these vortices were not contributing to the energy transport or to the heating, then these curves should be identical. Means whatever area they are covering, according to that, they should transport energy. But we can see that their energy transport fraction is much more than their area coverage. It means they are energetically important features. And the last part is just to show that this excess energy on the vortex locations is not because of excess magnetic field strength, because the magnetic field strength over vortices is similar to what is there on the other parts of the sun. So there is no excess magnetic field accumulation happening on the vortices. So all the excess energy transport that is happening is because of the plasma flows, not because of the magnetic field. And some other characteristics of these vortices. So I wanted to see how is the mass density. Is there any mass accumulation happening? So this is the average normalized mass density with height. And in upper atmosphere, you can see that there is more mass density over vortices than the average, because average corresponds to 1, and here it is like 50% more mass density over vortices than the other part of the solar atmosphere. So these rotational flows are actually dense in nature, and below and near surface they are less dense. And the reason for that is because they are originating in strong magnetic regions which are depleted of plasma. Because of the strong magnetic energy, there is less kinetic, the plasma energy, so there is less density. And to look at their contribution to heating, so I calculated the average temperature over vortices and the horizontal mean. So the solid curve here is the average temperature over vortex locations, which is more than the average temperature at each height. So that also tells that there is excess heating happening on these locations where there are vortices present. So the main conclusion from this part of the work is that we found in our simulations, there are various kind of vortex flows present, which correspond to different spatial and temporal scales. And we found that smaller vortices are actually much more abundant and short-lived than their larger counterparts. However, their spatial extent is too small to be detected with the current state-of-the-art observations. And statistically, they have higher density and higher temperature than their horizontal mean. And we also found that vertical Poynting flux is concentrated over these vortices. So they are a dominant contributor to the energy transport. And their mean Poynting flux density on the due to vortices is actually more than the requirement, the energy requirement to maintain these temperatures in lower, middle, and upper chromosphere. And for more details, you can follow these papers. I have actually much more things to discuss, but I will mostly stop here because I think I have taken all the time that I had. And yeah, so I would like to take more questions from your side. Thank you very much.
Any question from audience? Any question from online audiences? All right. So, thank you, ma'am. It was very informative.
Thank you very much.
Wonderful presentation. And they are in this learning phase. So like we haven't started the dissertation in MSc program. And this year we will start the dissertation programs where they will start learning the entire thing. And you have explained the entire basics, including the research also. So it's very informative lecture. Thank you, ma'am.
एक मिनट सिंटू रुको एक मिनट. Hello Nitin, very interesting talk.
Namaste, sir.
And let me tell you, Sintu, what you are doing is very nice, very well organized. There are few things which I want to ask if nobody is asking. Nitin, what are the equations you are solving here in your simulation?
So we are solving MSD equations, but in energy equations, we have a term for the radiation input. So that terms come from the radiative transfer equation. So in that radiative transfer equation, we include energy coming from within the solar convection zone, and also what is radiating out. So that term is solved separately. And a part of that, the induction equation. And yeah, these are most of the equations.
Mostly MSD equations. Actually, you were mentioning in your one of the slides that MSD waves are there, but there is no dissipation associated with them. For the dissipation, you have to go to the kinetic scale.
So about dissipation, we are not saying anything here, because for dissipation, we need to go to smaller scales. Only then the resistive dissipation and the viscous dissipation will will actually come into play. So all these simulations, so for example, in my case, I have a special resolution of 10 kilometers. But if you look at the Reynolds number in these places, then that is so high that the actual dissipation will take place at the scale of a few centimeters. And we cannot go to those scales. So all these simulations are actually large eddy simulations. So whatever energy is going below these 10 kilometer scales, that will be dissipated. We have artificial diffusion, so numerical diffusion.
So you introduced artificial dissipation.
Yes, yes.
By viscous damping or something like that.
Yeah. So we have terms for the numerical viscosity, and that terms come in both the momentum balance equation as well as the mass balance equation.
Oh, and what is your simulation scheme?
So in the first part, okay, so I didn't tell about the second part. So the first part uses finite difference schemes like, and second code that I didn't talk about, that actually uses finite volume methods.
Finite volume. Okay. So finite difference and finite volume. Okay. All right. And how do you test your algorithm for accuracy?
So there are, whenever we make any changes, we need to compile it again. And in that compilation, there are several tests that it has to pass through. So they have their already tested results. It will compare it with those and see how much error we are producing. And if that error is below a certain threshold, then it will continue. So for all these MSD codes, there are several tests available. For example, like this. There are several well-known tests that it has to pass through for a MSD code to be able to use to apply to MSD cases.
Like some conserved quantities or something like that.
Yes, I don't remember the name of the test right now because they are already, there are several tests, and whenever we make any changes, we compile it again, and if everything is fine, then it will pass all the tests.
Okay, very good. Thank you very much.
Yes, sir.
Thank you, sir. So, okay, ma'am, thank you.
Thank you very much.
Absolutely.
Thank
Yeah.
you for inviting me.
Thank you.